Hi, what I would like to show you is my newly constructed device. It's a solar positioning testing station, SPTS as I call it. The device is essentially a solar tracker with extended capabilities. SPTS was designed and built as part of my honors project at the University of Dundee, and it has the aim to help me analyze and find the dependency between positioning precision of a solar conversion device and its energy availability. As you know, tracking the sun makes your system more efficient in any way. I would like to know how do you have to track the sun in order to have a certain efficiency? How feasible is tracking, etc., etc. I would also like to analyze different tracking methods. There are tracking methods based on astronomical algorithms by which one could compute the sun position based on terrestrial time and spatial coordinates, and position himself towards the sun based on this calculation. The other way, the most obvious way to actually position yourself towards the sun is to just use analog methods, so to just use sensors and to, in quotes, see the sun and position yourself in this way. Now I would like to analyze both methods, which is better, which is not better, what can be used for what system, etc., etc. Many interesting aspects of basically solar energy engineering. The system here has two motors, one zenith and one azimuth motor, so it is an elevation and azimuth tracking device. The zenith motor has a step precision of 0.075 degrees. The azimuth motor has a step precision of 0.03 degrees. This gives me a very high resolution, and I can really hunt the sun quite precisely. I hope. I just constructed this device, so I'm currently testing it. The control over the device is made using the Rabbit microcontroller. It is an RCM 5600W microcontroller, which has huge capabilities. It is a web server itself. It connects to wireless networks if they are available. As a web server, it can be a client web server, meaning that it can contact other servers and ask them for certain things, and the other servers might respond to them if they are pre-programmed to do so. What else you see on there is onto the SPTS device is a New Haven display, 4-line 20-character alphanumeric display. This here is my development board. It's nothing really big, just a board. Below it, you can see the Rabbit itself. They're connected via USB to my PC. As you can see, there are some fluctuations, some bad connections on the display. I have some buttons here for manual control over the device, but if I want to control the device over the net, I can do so based on the Rabbit web page. So when the Rabbit loads up, when it connects to the internet, it loads a web page, which I pre-program as well. And through the web page, one could do anything really with the Rabbit, which could be done manually or through Dynamics-E. Best thing about it is that if I wanted to operate in, I just want it to be properly adjusted. If I wanted to operate in autonomous mode, which means basically it doesn't need to be a person or a client or somebody on the web server in order for the system to work, or somebody in front of the system in order for it to work. I set the system up so it contacts a PHP server on the web. And the server itself has written loads of astronomical algorithms on it. So the Rabbit contacts the PHP server and asks the PHP server to compute certain algorithms. By doing so, it sends to the server certain data containing basically the time and spatial coordinates of the system, and the server will send back the precise solar position based on a certain algorithm that as well was chosen by the Rabbit. In this way, I really extend the functionality and flexibility of this device immensely, because I can really program anything onto the PHP server, and then the Rabbit just needs to ask for a certain function. The server would compute it and send the results back, which is very cool. The test that I'm currently conducting and that I want to show you is the positioning precision of the device. On top here, as you can see, I've mounted a small laser, which is just a toy laser that I got from a £1 shop. The laser points towards a whiteboard. On the whiteboard, as you can see, I've set the laser to be in the 0 of this cross. Yeah. So this is my 0, 0 reference point, 0 azimuth, 0 zenith, and from this point I will, well, start now with the test. I'm gonna move 30 degrees azimuth, 30 degrees azimuth, 30 degrees zenith, increase a bit elevation, go back to 0, 0 and repeat the test many times just to see how the precision will deviate. Oh, I should say this as well. If there is an error during motion, during these repetitive steps, the error will eventually sum up and will become large. So therefore, I need to make a large number of steps to establish this deviation. So let us start with system F9. System starts moving, 30 degrees azimuth, 30 degrees elevation, going back the azimuth, going back elevation. So just a close-up of the system as it moves. This is my telephone just on top, by the way. I don't keep it there for advertising purposes, just keep it there because it's convenient. Okay, so this is the system moving. Sorry for the delay. We go now towards the board. Well, the point is right now there, moves up somewhere here on the roof, and now it's gonna come back. I'll let you know. Okay, right now, up. It moved about half a centimeter to the right, as you could see. Now again, there we go. Moved, yeah, about half to 0.8 centimeters is what I've measured for about 100 tests so far. Conducted repeatedly, and as you can see now we are on test 7 only, because I just started for this video. But it really stays there. It stays between 0.5 and 0.8 centimeters of deviation. And in this way, when I just calculate the distance between the device and the whiteboard, it's about 3.5 meters. And the deviation of 0.5 to 0.8 centimeters. By Pythagoras, this gives me an error of approximately 0.02 degrees, which is very low, which is much better than I was hoping. Of course, this is a very controlled test, and sorry, the laser just got disconnected. Okay, this is a very controlled test, and I do only this sequence for now. I just go from 0 to 30, 30, go back to 0, 0. When the randomity in the movement increases, the error will be larger, I guess, I suppose. Therefore, I will conduct many other tests for which I will let you know in case you have interest. So thank you very much and bye-bye.